Hello and welcome back to the deep dive. Sometimes the most crucial bits of our digital world are the ones working away behind the scenes, connecting our favorite apps, our services in ways we maybe don't even think about. They're kind of like the invisible glue holding the internet together, making everything just work. So today, we're going to peel back the layers on one of those really foundational elements. Yeah, we're taking a deep dive into the world of API design patterns. Okay, so APIs, application programming interfaces, think of them as like universal translators. They let different bits of software talk to each other. And like any good conversation, really, the clearer the rules are, the better things work out. Our main source for this is Kat Rafalski's really insightful article, API Design Patterns, Best Practices for Building Scalable Interfaces.
It's pretty amazing when you stop and think about it, isn't it? I
Right.
mean, most of us, we interact with APIs all the time. You check the weather, you order groceries online.
Yeah.
But we rarely consider the actual deliberate design that goes into making them work. So this deep dive, it's really about understanding those proven solutions, the thoughtful choices developers make. It's all geared towards creating better, more consistent, and ultimately just easier to use digital interfaces. It's kind of a shortcut to getting smart about this, silent architecture of our digital lives. Gives you a whole new way to look at how your favorite online tools actually connect.
Right. So our mission today really is to figure out why smart API design makes developers happier, leads to fewer errors, and creates systems that just, well, grow better over time. You'll walk away understanding not just what an API is, but why these design patterns are so essential for making our digital world faster, safer, and way more reliable. Okay, so let's start right at the beginning. The article talks about an API at its core being like a contract between different software systems. What does that actually mean, like, in practice?
Yeah, that contract analogy is really, really good. Imagine, say, two companies need to work together. They'd write up some agreement, right? Defining what services each provides, what info they'll swap, the format. An API is basically the digital version of that. It clearly lays out the specific methods, the data formats, the rules for how they interact. And these interactions, they often use standard internet stuff like HTTP to move data around. Each request usually has a method, get, post, put, delete, and a specific address and endpoint URL. Those bits plus details like maybe authentication tokens tucked into the request headers, that's fundamentally how these systems, digitally shake hands and talk. Okay, so it's really about setting crystal clear expectations. Got it. And when we talk design, one of the most common sort of standardized ways to build APIs is REST, right? Representational state transfer. Why has RESTful API design become so, well, everywhere? What's the big deal? Well, the real beauty of REST, I think, is its simplicity and how well it scales. It works using what's called stateless communication. That means every single request has all the info needed to process it. The server doesn't need to remember past interactions. And it's resource-based, meaning everything a user, an order, whatever, is treated as a resource with its own unique URI. That's Uniform Resource Identifier, basically its web address. The power isn't just that it's predictable. It's how this stateless thing lets really big distributed systems scale up massively, almost infinitely, really. Because each server doesn't need this huge memory of past chats. Think of like a busy restaurant where every order is totally fresh, no need to track what you ordered last week. It makes the system super robust, less likely to fail if one server hiccups. This uniformity, plus using standard HTTP methods for actions, makes REST APIs incredibly predictable, consistent. And that's absolutely vital for developers trying to build stuff using them.
That makes total sense, like a self-contained conversation every single time. But okay, looking beyond just one API, how do these pieces fit together? Especially in really complex systems, how do they support scaling up and being maintained? What does that bigger API architecture tend to look like?
Yeah, well-designed API architecture is, it's the backbone of any digital system that needs to grow. One really key component you'll almost always see is an API gateway. Think of it like the main traffic controller at the entrance to a digital city. All the requests come through it first. It figures out where to send them, which internal service needs to handle it. And it also does things like security checks, rate limiting, stopping too many requests before the request even hits the main applications.
Ah, okay, so like a bouncer and a receptionist rolled into one, handling the initial stuff. What else helps manage all that traffic?
Then you often have load balancers. These are absolutely essential. They spread the incoming traffic across multiple servers. So this stops any one server from getting totally swamped, keeps performance consistent. It's like having, multiple checkout lanes open at the supermarket during the evening rush.
Right, smart, avoids queues.
Exactly. And to speed things up even more, you've got cache layers, these store responses that get requested a lot. which means the system doesn't have to generate the exact same data over and over again. That can drastically cut down response times.
That makes sense. Why redo work you've already done? Okay, what about keeping all this info safe? Security must be huge.
Oh, absolutely huge. There are strong security layers woven throughout. They handle authentication, basically proving you are who you claim to be, and encryption, which scrambles the data so only the right people can read it. And increasingly, you see modern APIs using microservices. This means breaking down big, complex applications into smaller, independent services. Each service handles one specific function. This lets different teams work on different parts without, tripping over each other. It leads to massive scalability and makes maintenance way easier. Plus, it helps keep sensitive data more isolated and protected.
It's like building that city with really well-defined districts, yeah, each one handling its own specific job. And a big part of that robust setup must be defining everything clearly right from the start. The article mentions API modeling and specification, specifically something called Open API. Can you unpack that a bit?
Sure, API modeling is all about creating these structured designs before you even start coding. It's about really nailing down exactly what your API is going to do. This means things like giving clear, descriptive names to the API endpoints like users for managing user accounts or orders for handling purchases, and specifying exactly which HTTP methods they'll accept, what data formats they expect to get, and what they'll send back. The really clever bit, as you mentioned, is how OpenAPI, which used to be called Swagger, standardizes this whole thing. It creates this definite contract between the API provider and whoever's using it. It documents everything, data types, authentication methods, you name it. This specification, often written in a format like YAML or JSON, becomes the single source of truth. And this document is so powerful, you can even use it to automatically generate interactive documentation for developers or even starter code for them to use. Really cuts down on misunderstandings and speeds up development time.
I love that phrase, single source of truth. Sounds like it prevents a lot of headaches down the line. Okay, let's dive into the heart of it now. The actual API design patterns and best practices. These are the tried and tested solutions that templates developers lean on, right? What are some of the really common ones?
Yeah, absolutely. They're the foundations for building interfaces you can rely on, that you can maintain. The resource-based pattern is probably the most intuitive one. It organizes the API around core business things like products or customers or orders. Makes the API really easy to understand and navigate. Then there's the pagination pattern. This one's vital when you're dealing with huge amounts of data. Instead of trying to send back like millions of records all at once, which would be super slow, it breaks them into manageable chunks or pages, improves response times and the user experience dramatically.
Like flipping through pages in a book instead of trying to lift the whole bookshelf at once?
Yeah.
Yeah, okay.
Exactly. Perfect analogy. And then you have CRUD operations. That stands for create, read, update, delete. These just offer a standard, really predictable way to interact with those resources we talked about. Most things you do online, adding something, viewing it, changing it, removing it, fall into one of these categories. And finally, there's the facade pattern. This one is great for simplifying really complex backend operations. It hides all that internal complexity behind a cleaner, simpler interface. This makes it much, much easier for developers who are trying to use your API. Lowers the learning curve significantly.
So a lot of it is about making things intuitive, manageable for the developer using the API. Beyond those core patterns, what other key best practices help ensure things stay consistent and make an API genuinely developer-friendly?
Right, so beyond the specific patterns, the best practices are really about discipline and thinking ahead. Using clear, descriptive names for everything, your endpoints, the parameters you pass in, that's just fundamental for clarity. Keeping responses focused is important too. Only send back the data the client actually asks for or needs. That also helps speed things up. Really robust error handling is critical. Using the right HTTP status codes and providing meaningful error messages helps developers debug when things inevitably go wrong. It gives them a clear pointer.
Instead of just error occurred.
Exactly, something useful. And then for the long-term health of the API, versioning is basically non-negotiable. It lets you evolve the API, add new features, fix things, without breaking the applications that already depend on the older versions. Ultimately, it's consistency and standardization across the board, URLs, methods, how responses are formatted, combined with really thorough documentation that transforms a merely functional API into one that's genuinely a pleasure to use and can scale effectively. Oh, and using standard data formats like JSON helps a lot too.
Yeah.
It makes the API accessible from pretty much any programming language or platform out there.
Yeah, JSON definitely seems to be the king of data handling these days. The article points it out as the most widely used format. Why is it so dominant? And what are the best ways to work with it, especially if you're dealing with large amounts of data?
JSON's popularity really comes down to its simple, readable structure. It uses key value pairs, which is super easy for humans to read, and just as importantly for machines to parse or understand. It's lightweight, it's flexible, and pretty much all modern programming languages support it right out of the box. Best practices. Well, consistent naming for your JSON fields is key. Usually you see either camel case like first name or snake case like first name. Just pick one and stick with it throughout your API for predictability. You also need to think about setting size limits on the JSON payloads, the data chunks being set to stop servers getting overloaded, maybe somewhere between, say, 1 to 10 megabytes typically. And when you are dealing with large data sets, that pagination pattern we mentioned is absolutely essential, often using parameters like limit and offset in the request. So you might ask for .limit 20 and offset 40 to get the third page of 20 items. Similarly, filtering lets clients ask for just a specific subset of data, like .category electronics. And sorting parameters let them organize the results, maybe .sort created date .desk, the newest first. All these methods are really about preventing either the client or the server from getting swamped with too much information all at once.
Right, making the data manageable. And for managing it, those HTTP methods you mentioned earlier, get, T, post, boot, T, delete, they're really like the verbs of the API language, aren't they? They map directly to those CRUD operations you talked about.
They absolutely do. And that mapping provides this clear, consistent grammar for how clients interact with resources.
Sure.
It's incredibly useful. So for example, if you have a library API managing books, you'd use DGT books to list all the books. You'd use POC books to add a new book. POT books 123 might update the details of book 123. And delete books 123 would, well, remove it. This predictability is just super powerful. Once you understand these basic verbs, you can figure out how to interact with almost any well-designed API out there.
And then after you make a request, the API needs to tell you what happened. That's where HTTP status codes come in. They seem like more than just numbers. They tell a really important story, don't they?
Oh, they're crucial. Absolutely crucial for effective communication. Think of them as instant feedback. The 2XX codes like 200 OK or maybe 201 created, if you just added something, they signal success. Everything went perfectly. The 4XX codes, they indicate a problem on the client side, like 400 bad request if the request was malformed, or 401 unauthorized if you didn't log in correctly, or 404 not found if the thing you asked for just doesn't exist. It's kind of the API saying, hey, I understood what you wanted, but you made a mistake somewhere.
Okay.
And then the 5XS codes, like 500 internal server error, they point to problems on the server side. Uh-oh, something went wrong on my end, not your fault. Using these codes correctly and consistently helps developers incredibly quickly figure out what went wrong and fix it. Makes the whole system way more robust and ultimately user-friendly.
Makes sense. So with all this communication happening, keeping things secure and stable must be paramount. How do APIs protect themselves from getting overwhelmed or misused? And how do they keep performing well when lots of people are hitting them? The article talks about caching and rate limiting here.
Yeah, API security and stability involve several layers working together. Caching strategies, as we touched on, significantly cut down the load on the backend servers and improve response times by storing data that gets accessed a lot. Think of a popular news website. Instead of building the homepage from scratch for every single visitor, it can store a ready-made copy for, say, a few minutes and serve that up much faster. Responses from the API often include special cache control headers that tell the client or intermediate caches how long they can safely store that data. You set a time to live, or TTL, for cache data, basically its expiry date. And you can use things called E-tags, which are like unique fingerprints for the data, to quickly check if the cache version is still fresh without needing to re-download everything. Really boosts performance.
Okay, that covers speed. What about preventing abuse or just accidental overload?
Right. That's where API rate limiting comes in. It's super important. It controls how many requests a specific client or maybe an IP address can make within a certain time window, like, say, 100 requests per minute. This stops any single user or a buggy script from overwhelming the API and making it slow or unavailable for everyone else. These limits can be quite sophisticated. They might vary depending on, whether the user is logged in, maybe what subscription level they have, or even how computationally expensive a particular type of request is for the server to handle. And often, the API will cleverly include rate limit headers in its responses, telling the client how many requests they have left in the current window and when the window resets. So clients can actually track their usage and back off if they need to. It's all about ensuring the API stays stable and available, even when it's under heavy demand.
So it's about protecting the API, keeping it running smoothly, while also making sure it can change and improve over time. Because APIs aren't set in stone, right? They need to evolve. How do teams manage these changes without breaking all the existing apps that depend on them? This brings us to versioning and lifecycle management.
Yeah, this is such a critical area because without a good strategy here, any API would just become a tangled mess really quickly.
Yeah.
API versioning strategies are what allow APIs to evolve. You can introduce new features, make breaking changes maybe, without disrupting the existing applications that rely on the older versions.
Mm-hmm.
You often see versioning right in the URL, like V1 users for version 1, and then later V2 users for version 2. It's called URI versioning. It's very explicit. Other ways include using custom HTTP headers to specify the version, or maybe query parameters like users.version1. The most important thing is just being consistent with whatever strategy you pick. And versioning is really just one part of a bigger picture called API lifecycle management. This means planning everything from the initial design idea all the way through development, deployment, maintenance, and eventually maybe retirement of the API or specific versions. It involves tracking who's using the API and how much, doing regular reviews, and crucially, keeping documentation up to date and providing clear change logs so developers know what's changed between versions. Having this foresight prevents massive headaches and really costly disruptions later on.
It definitely sounds like planning for the long haul. Okay, so as an API gets more popular, handling more traffic, keeping things fast, those become huge challenges. What kind of design patterns or optimizations ensure an API can scale smoothly and still deliver speedy responses?
Well, designing for scalability often starts way back with deciding on smart service boundaries. Breaking big systems down into smaller, independent microservices, as we mentioned, allows each part to scale up or down individually based on its specific load. Load balancing, again, is key for distributing traffic effectively so no single server becomes the weak link. And leveraging caching aggressively for frequently accessed data takes a huge load off the underlying databases and services. Now, for performance optimization, making data retrieval efficient is vital. This could involve things like batch requests, where a client can bundle multiple operations into a single network call. That cuts down on the back and forth network overhead. Using compression, like dzip, reduces the actual size of the data being sent over the wire, making downloads faster. And asynchronous processing is really powerful too. It lets you move time-consuming tasks like generating a big report or sending emails off to background workers. This keeps the main API thread free and responsive, ready to handle new incoming requests quickly. All these strategies, they're about squeezing out maximum efficiency and ensuring the user gets that snappy, responsive experience they expect.
That leads nicely into the bigger picture, especially with microservices. How do all these separate independent services actually talk to each other effectively? It sounds like it's not always just a direct call from one to another, right? We need specific integration patterns.
Precisely. Yeah, in the microservices world, things get more complex. The API gateway often acts as that central entry point, like we said, but it also plays a role in routing requests to the right internal service. And it handles cross-cutting concerns, like making sure only authenticated users get through. But for communication between the services themselves, you often see a mix of approaches. Sometimes synchronous REST APIs are fine, especially for requests that need an immediate answer. But for handling high volumes of events or tasks that don't need an instant reply, asynchronous messaging patterns are really common and often better. Each microservice exposes its own well-defined API, and ideally they all follow consistent standards for things like HTTP methods, error handling, and how they do versioning.
And you hear the term loosely coupled integration a lot in this context. What does that actually mean in practice? How does it help?
Loosely coupled integration is a core principle here, yeah. It means services communicate, often through exchanging messages, without being tightly linked or directly dependent on each other's internal workings. This is huge because it allows individual services to evolve, to be updated or even replaced independently without causing a cascade of failures throughout the whole system. Think of it kind of like a public bulletin board. One service posts an event message, say, order created, to the board. Any other service that cares about new orders can subscribe and read that message. They don't need to know who posted it or even who else might be reading it. Tools called message brokers like Kafka or RabbitMQ often facilitate this kind of reliable asynchronous communication. The really critical element, again, is having clear service contracts. These define exactly what inputs a service expects, what outputs it produces, and its basic behavior. And using systematic versioning like semantic versioning for any changes to these contracts is vital to maintain compatibility. This whole approach builds incredible resilience and flexibility into the system.
Okay, we've talked a lot about external APIs, the ones facing outwards towards users or other companies, but lots of companies also have internal APIs, right? The ones their own developers use to build internal tools or connect different internal systems. Is there anything special about managing those? And maybe more importantly, how do you improve the experience for the developers who are actually building with these internal APIs?
That's a great point. Internal APIs absolutely need strong governance too. You need clear rules and standards for naming things, for versioning, for documentation, just like with external ones. You can't just let it be the Wild West internally. API gateways can be really useful here too, helping monitor internal traffic patterns and enforce security policies even within the company network. And obviously, proper access controls and authentication are still vital. You need to protect sensitive company data while still empowering the developers who legitimately need access. The goal, just like externally, is always to avoid breaking changes if you can, and to communicate any updates really clearly, often through internal change logs or developer portals. Now, when it comes to improving the developer experience, or DX, as it's often called for those internal teams using the APIs, that's super important, maybe even more important sometimes. It means providing excellent interactive documentation, maybe auto-generated from those open API specs we talked about. It also means providing software development kits, SDKs, or client libraries in the main languages your internal teams use.
These are like pre-built toolkits that make it way faster and easier for them to just start using the API without writing tons of boilerplate code.
Ah, so giving them a head start.
Exactly. Developer portals can centralize all these resources, the docs, the SDKs, maybe tutorials, and giving developers easy access to things like monitoring tools so they can see how their usage affects the API, or mock servers and sandboxes so they can test their code safely without messing up live systems. All that really helps them build faster and identify issues early. Fundamentally, happy, productive internal developers lead to better quality software, which benefits the whole company.
And that brings us pretty much to the end of our deep dive into API design patterns. Wow. We've really covered a lot, from that basic idea of an API as a contract right through to the really careful strategies for security, scaling up, and yeah, making life easier for developers. You've hopefully seen now how these sort of hidden heroes truly shape pretty much all modern software development.
Yeah, ultimately, when you boil it all down, what we've really been talking about is the art, and maybe the science too, of digital communication. Good API design, it isn't just some minor technical detail. It's fundamentally about clarity, it's about predictability, and it's about building trust between different systems. It's making sure that when, say, your banking app needs to talk to your payment processor or your smart thermostat talks to the cloud service, that conversation is efficient, it's secure, and it's perfectly understandable by both sides.
So what does all this mean for you listening? Well, maybe next time you use an app that just feels incredibly smooth, really seamless. Or you notice how quickly a company rolls out new features that seem to work across their website and their mobile app instantly. You'll maybe have a newfound appreciation for the really thoughtful API design patterns working away behind the scenes there. It's kind of a testament, isn't it, to how all this meticulous planning can make our complex digital lives feel surprisingly effortless.
And this whole conversation, it might spark a question for you to think about later.
Yeah.
As more and more of our lives get digital, get interconnected, how might these principles, we've talked about things like consistency, clarity, versioning, how might they apply in other areas where communication is absolutely key? Maybe within your team at work, or in a community group, or even just in your personal interactions. How many sort of hidden contracts or unspoken rules are actually at play in your daily life? And what happens when they're well designed? Or maybe when they're not.
Yeah, something to think about. Keep an eye out for those little signs of good design or maybe bad design in the apps and services you use every day. We really hope you've enjoyed this deep dive into the pretty foundational world of APIs. Until next time, keep learning and stay curious.